在这个答案
另外
这边就是长按，然后插入空在页份，要的话就
这个答案呢？完成吗？
刚放好，确认一下。
没有上传哦。结果有一这里哦，可以点它，才会连上去哈。没有关系，再试试看。First, actually, last week I have described some theory, right? Yeah, this is important important criterion. For sampling theory. So let's go back to look at signal system. If you have a question, try to read previous video. Okay. So I will go through very quickly. So image you can see, please read by yourself because it's come from different EM waves. And you can observe different quality of image and different type of image like this one. So it's energy of the photon. So the image theory actually the image of EM wave, different electronic magnetic wave, and it has different frequency spectrum. Yeah, you can see from the radio wave, then microwave, infrared, and then visible red band, only very small segment of all the EM spectrum. And then some ultraviolet, X-ray, gamma ray, blah, blah, blah. So it depends on the photon transmitted in the air. And when the frequency is higher, and it's harmful. But lower than the visible spectrum, I think it should be very safe for you to observe, expose yourself among these different EM wave environment. So if you want to look at more detail, please look into this website. This is the EM wave spectrum. and we see it's depend on your wavelength of your signal. So the visual band is only very small band. Okay, you can visual it because it's limited to your eyes. Different animals have different visual spectrum. Okay, like dog during the night they have a better vision than human eyes. And yeah, when the signal is higher with higher frequency, it's become like ultraviolet, like a gamma, like a X-ray. So it's harmful. They can penetrate through a lot of different material, like a lead, like a different material. They can penetrate. So it's harmful for the high frequency with very high energy. So how to calculate the energy? So you can see every photon in the air, and their energy can be calculated by the constant Planck constant multiply your frequency. So when your frequency is high, your energy of the photon will be very high. Okay, so it's very traditional EM wave like this one. We said the gamma, they can penetrate alumina and even the lead. Okay, so with a higher energy, they can penetrate a lot of different material. So it's harmful for our body. So you have to escape for the high frequency wave environment. Okay, I think I'm not going to go through every detail of this image. It's just some different skill as equipment. You can observe different type of image from your real world application. So I just said you just have a cup of coffee and then take a look. Okay, yeah, I already reserved this textbook in the library. So you can go there and take a read. If you don't buy, you don't purchase this textbook, you also still can read this textbook in the library. Okay, it's reserved. See, if you have a different satellite and receive the image from the satellite with different band, even with the same, yeah. So for this one is the NASA Landsat satellite. Use a different visual band wavelengths to observe the image from the satellite, and you can see different band, different wavelengths with different band, like infrared, like the thermal infrared, middle infrared is all between this small wavelength range, and you can observe different results. Okay, from the same satellite, use different wavelengths to extract the image, and you can see from seven different ones, you can see different image. Okay, so you can see some biomass, some water, some different material. Actually, it's the same location, the Washington D.C. area, but use a different wavelengths to observe the image from the satellite. You can see, yeah, they just mentioned if you are interested in different moisture content, the soil, you are interested in biomass or mineral mapping, you can use different wavelengths to observe the image from the air. Okay, so this is satellite image on the same area. Yeah, so just take a look and you can see the hurricane, different light, blah, 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 blah. So I just quick go through this image, all different application in this chapter. So it's all introduction. You can observe different image from different band. Yeah, it's some fractal image. So summarize for this chapter, we just want to let you know. Actually, in digital image processing, we have different labels. Okay, like this one, we have four different labels here. And label 0, label 1 is image representation and also image-to-image operation. So your input is the image, output also an image for up to this level. And for the level 2 is image for parameters. So it's going to be visual expression. So it's not an image element. So you input an image, but your output is some numerical feature, maybe how many vertical lines, how many horizontal lines, what's the textual pattern, what's the density. So this is for computer vision application. This is for image processing. So this course will focus on the first two levels and teach you how to do some image operator in spatial domain, in frequency domain, but it's all image to image transformation. A lot of noise. This one? Yeah, okay, let's Okay. Oh, it's later. Yeah. So different choice. Okay. So the first chapter is quite easy. Please read the chapter by yourself. And today, the most important we are going to introduce is the fundamental of the image processing. So here, we want to understand the human vision, understand yourself, how your image go into your eyes, and how you observe the image, your human vision. We want to see image sampling and correlation. Actually, we are going to digitize the image from analog signal. So in the word, it's an analog signal, and then you are going to sample it, and then put into your eyes, and then you will observe it. Also use a computer to run the simulation. Also, we want to see what's the resolution and effect of the image appearance. As you know, we have a higher spatial resolution. What's the spatial resolution? It depends on how many pixels, how many pixel elements in the image you are going to accurately from your device equipment. So it's a spatial resolution. The second resolution is the intensity resolution. How many grade level you are going to observe in your image for each pixel. For example, we have a 256 grade level, right, for one pixel. We also can have a binary image. It's only two grade level, 0 and 1, right? So different grade level, different intensity level also have different resolution. So we are going to discuss what's the resolution and effect of the image appearance. So in your intuition, you will say higher resolution should be better, right? Is that right? Higher resolution. Okay, so if you look at it, the digital image, we have a very small resolution, like a 640 by 480, very traditional video frame resolution. And now you have more than 1,000 resolution, 1028 and 768. 1028, right? 1024, right? 728. So which one is the better in your intuition? The high resolution give you a high better image quality, right? How about the intensity resolution? 4 grade level, 8 grade level, 64 grade level, 128 grade level, 256 grade level. Which one should be better? One should be better. In your intuition should be higher intensity resolution should be good. The quality should be better, right? But later on, we will show they have some relationship with your image content. So not exactly what you think. So you will see some experiment result there. So later on, we will also check the geometric relationship between the image processing. So today we are going to learn what's the Cannet component, how you process your image at the first step. Okay, so we are going to give the first homework. And you have to write a program for Cannet component and label it for the subject in one image. It's very important to do the first image processing. We are going to see how many objects in your image, and you are interested to solve the problem to do some pattern recognition. For example, like OCR, we mentioned this example before. So you have to extract all the Cannet component image in this image, and then to do some pattern recognition or character recognition. So these are geometric relationship you have to evaluate. So we have to learn some terminology. First is neighboring. How you define the neighbor of the pixel. And then we are going to decide it. They are connected each other. And then we are going to label it with some object. And then you can extract the image from this one and do some pattern recognition. Okay. Yeah, this is today's procedure. So the first one was your eyes, your eyeball here. Okay, imagine. Okay, so it's they have three layers in your eyeball. The outside of layer is a cornea. Cornea outside is a kind of heart. Cornea, and then connect to sclera. Okay, it's, I think it's Greek word. Sclera or sclera. Okay, and this is cornea outside to this one. This is opaque. It's not transparent, but the cornea is transparent. Okay. hard one and softer one. So it's the off layer, off layer of your eyeball. And then the second one is the choroid. Okay, inside the sclera is a choroid. So the choroid is a lot of blood vessel, the nerve connect all these oxygen and nutrition for your eyes. Okay, so the second layer, choroid. Excuse me, I can use Chinese for part of the Taiwanese student. 角膜、巩膜、脉络膜 is kind of membrane. Okay, choroid. And the inside layer, we can see the retina. 视网膜. Okay, so you have three layers basically in your eyeball and from outside to inside. The retina inside, they have a lot of receptor here. Okay, everything you can see is actually is a receptor connect to nerve and then transfer to your brain, and you will understand, recognize the object you are going to learn. So in this area, they have different inside the retina. On the retina, they have a lot of different receptors. Actually, we have two different types of receptors. The first one is cone here. Cone receptor, 小锥状 kind of 接受器 receptor. And the cone receptor is for the bright vision. When you sit here, look at this bright vision, a lot of light. So your eyes, the cone receptor working well. For the other one is called rod receptor. Rod is like a 柱状, and so it's for the dim vision. During the night, you are going to look at something. Your rod receptor will work well. So we have two different types, the cone and rod receptor on your surface of retina. Okay, 在视网膜上面retina, a lot of different cone receptor, rod receptor. Okay, the cone receptor have around 6 million receptor, and every single cone receptor connect to one nerve end for the bright vision. Every cone has its own nerve end. But for the rod receptor, several rod receptors connect to one nerve end. Okay, that's the vision you are going to observe anything. And here you see there's a blind spot. So this is for the nerve penetrate through this one. So blind spot. There's no receptor, no cone, no rod. So it indeed happen. 盲点 actually it happen in your eyes. And there's an important area we call fovea. The most cone receptors concentrate on this area. So when you look at something in front of you, the most of the image will be observed by this receptor here. So the distribution of the cone receptor is much higher than other where. So fovea is a central location. Okay, 中央凹in the center. So if we can see the distribution of the cone and the rod receptor. And you know the lens, right? The lens is a transparent, and we can observe a lot of violet and infrared, a lot of dangerous light. And we have this iris. Iris can automatically contract or loose during different light, and it's between 2 millimeters up to 8 millimeters. So iris is can like a automatic door to protect your eyes, and then the light penetrates from through the lens. And when you're getting old, the lens will become yellow. Like me, I already changed my lens. Okay, to watch too much computer. So please protect your eyes when you are young. Okay, so let's look at this one. This is I told you actually it should be a round shape, right? Like a ball, round shape. Okay, this one is a fovea. Here we just mentioned this is a 0 degree, and we have different degree around this center of your eyes, and you can see the receptor here for this solid line is a cone receptor. A lot occur distributing in this area for the bright vision, and the dotted line is a cone a rod receptor. So it's around the fovea. So it's for the thin region, night region. And unfortunately for the fine region here, there's no receptor. Okay? This is right eye distribution. Left eye will be symmetric. Okay, so just give you a very quick idea about the receptor in your eyes. Okay, so we have a different layer of your eyes, and every layer has different function. Yeah, and you actually reserve the image just like that. And what's the size of the image you observe from the distance, maybe 100 meters away? And there's a palm tree, height with 15 meters. And then project to your eyes at the bottom of this fovea, and you can calculate that mathematically. This divide compared to this one, and go to this one compared to this one. And your eye axis is about 1.7 centimeter, 70 millimeter. So you can calculate there's a 15-meter palm tree inside your eye. It's around 2.2 millimeter. Okay, so it's the way you observe the image. Okay, so let's look at this brightness. Is that linear in your eyes for the human vision? So now we know we have two different type of receptor. One is cone for the bright vision. The other is a rod for the thin vision. And you observe the intensity simultaneously around your environment. Unfortunately, the answer is no. Even this solid line is for your topic. It's a cone vision. The range is huge. Okay, this subjective brightness. Actually, you can observe different light intensity. However, in the real life, when you focus on something, your vision becomes only part of it. You cannot observe the wide range at the same time. Okay, so you look at some vision, and then their brightness or topic, the bright vision, only limited here. So even the lighter or darker, you cannot make any difference of it. You cannot discriminate the lighter, the darker. No way. So even you can see it, but once you look at some specific intensity level there, your region becomes dynamic, only limited in certain range. Okay, so they have do some experiment on your eyes. Yeah, so this is a topic region. Actually, you only can observe your rod, only can observe this brightness around this area. Okay, so the cone vision has some limitation. You can see something, and when the background change, the light change, you cannot observe it. What's the differences? Okay, so they have do this experiment. So this is experiment set up used to calculate the brightness discrimination. So you can go back to check this one, perform the experiment by yourself. So this is background image. So you look at some variable with the intensity level I. Okay, and this is the hole, the penetration hole, and you put some different light here. Okay, and the central hole is of the different intensity level. So you are going to increase it, and then when you see the difference, you say, yeah, they are different. You can see the center intensity different from the background. Okay, it's very easy. Very right. The background intensity, and the center you can in the center hole you can modify the intensity level by adding some different intensity, make it lighter, shinier, and but unfortunately we will see the What's the result? Can you understand the experiment? Try to evaluate your eye and how you adapt your eye to the brightness, different intensity in label and environment. Result like this one. Actually, I have seen some different results for a higher brightness, like the U shape there. Okay, so this is the home vision. This is for field vision. Okay, you read the book, they will tell you. So when the light, this just tell you it's not linear. Okay, so it's a typical plot of the Weber ratio. The previous one is the Weber ratio. Delta I divided by A. We are going to look at the Weber ratio here. And actually, it's a function of the intensity level there. So when your eye darker and you want to see more different, and you can say, they are different because you change the light there. You need more change here. Delta I should be larger. Okay. So when your background is darker, and you are going to tell the difference of darker, you can change a lot, and you can observe the difference. That's the idea. Even in the higher shape there, again. So you need to make larger difference to feel the discrimination between the background and the central light, central intensity. Okay, that's just the idea here. Okay, so here you don't need one, and this one is much higher. The slope, okay, you can see the slope. And here, maybe only a little bit change, you can say, they are different, right? But when it's on different intensity level, you adapt to different brightness. They need to add different level of intensity to make your eyes feel the differences. We call it the Weber ratio. Okay, now we're going to test your eyes now. Okay, let's see. So this is the gray level image for 6 different gray levels. Can you tell me, how about the age? You see the age, right? For different gray levels. Can you tell me the color of the age in left-hand side and right-hand side, are they different? Okay, so maybe let me ask you a question. Can you see this darker gray level than this one, all stripe intensity level? Can you see that? No? You have good eyes. I don't believe it. When you look at it, the edge color, you will see in the edge, the left-hand side of the edge, darker. Right-hand side of edge, shinier, brighter, compared to this color. Can you see the shiny edge here? No? How about this one? You think the light here, right-hand side, there should be a lighter. Close to the edge, become darker. About this difference? Right? But unfortunately, I will have to tell you the truth. The intensity level exactly the same in this width, all the same intensity level. Here, all the same intensity level. Here, all the same. That's the intensity level. But your observation should be like this. Here is darker, lighter. Here is darker. Here should be darker, should be lighter compared to background image. Can you see that one? If you can see if you are reading like this one, you are Superman. But for the normal people, should be observed like this one. Darker edge, lighter edge on right hand side, darker on left, right? Okay, thank you for agreeing with me because it's very obvious for me. The right hand side of the edge is lighter, okay, compared to the background image. But the left edge is darker compared to the left stripe, right? Should be, right? But if you just, what can I do? Okay. Now you can see they are exactly the same, right? The gray level exactly the same. But if I put together, sorry, they look different. look brighter, right? Look brighter here. So this is common eyes. Your eyes will help you to do some simultaneous contrast and perceive image intensely from exact image. Okay, so we are human. How about this one? Could you please compare the intensity level inside of three image, the inside small square? Which one is darker? Which one is lighter? The same, but not human being. Are you sure? Yeah. But tell me the feeling. Which one is darker? Darker. The inside box. Which one is darker? Yeah, it looks like darker, right? You have to tell the truth. The answer, you are right. They have exact the same grade level, exact the same intensity level. But if I put that together, cannot tell me they are exactly the same intensity level, right? They just look darker than this one, than this one. You compare this one and this one, right? It looks darker, right? You understand? Okay, they should be. So it's called simultaneous contrast. When you compare each other, your eyes will give some different feeling, psychological feeling to the image. Even I put the same. But if you look at clearly, they are exactly the same grade level. Just the background different. Background different. But if you compare them together, right? Just have a quick look. The right inside box must be darker than the other two. Okay, so we call it simultaneous contrast. The inner square have the same intensity but appear progressively darker when the background is lighter. Okay, so do you see a circle here? Your eyes tell you there's a circle. Your eye tell you there's a square, right? Square shape there. But you know there's no square, there's no circle at all. Okay. And how about this one? Can you tell me which line is longer? Which one is longer? The horizontal line? From your vision, the answer is the bottom line should be longer than the upper line, right? Fortunately, you understand. That is the same. I just put some different line there, and you will see the bottom line looks longer than the upper line, right? Maybe you are all women, but girl, and yeah. How about this line? Can you see? Are they parallel? Okay. If I do some different length line there, you will see they are not parallel. Like this two lines look like a taking quite open, right? But I don't know if I see on the far side, yeah, the same, yeah, the same feeling. They look far away, closer, but actually they are parallel, exactly same distance in the line, same distance. But you do some different line there. Your visual will tell you the different feeling, right? What's that? We say this is optical illusion. Yeah, optical illusion. Yeah. A lot of different example can tell us actually what you see is not what's the truth. So sometimes, yeah, you have to go back, think about that. Okay, so optical illusion there. Oh, this one we already mentioned. It's electromagnetic spectrum, EM wave. Our visual band only sitting in this very small range of the wavelength of the frequency band. And yeah, so it's a different way to see the spectrum. Okay, so, and here I want to describe more things about the wave is you have different EM wave in the air, and you can see it. How we quantize the actually we have a few different terminology you have to know. Basic quantity. The first one is radiance. Okay, radiance is the amount of energy flow from the light source. So actually you have the radiance and you will see it. If you don't have any EM wave there, you see nothing. Okay, so it's a radiance, the amount of energy. Okay. 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 The energy, amount of energy. And from the light source. So you need the light source to see something, right? So if you sit in a dark room with no single light source, you see nothing there. Okay, and it's we say the unit of the radiance of watt. How many watts? And the second one is luminance. Okay, so it's like intensity. Okay, and the unit is lumen. So it's amount of energy. Amount of energy an observer perceived. PEIEVE. You can perceive from a light source. Okay, so you have these two basic quantity there, and later on we are going to use this as to calculate what the intensity level comes from. Actually, you need a light source and you need a reflectance of the object. Otherwise, you see nothing. Either one of them, you need some value there. Okay, what is the light source? And then the light source on the object you observe. There must be some reflection, and then you will see something. So our intensity levels come from I times reflectance of the light. Okay, so different frequency waves, like red, orange, yellow, green. We have different frequency, right? Different wavelengths. And put on the light source, put on this object, and then into your eyes, you observe it. So if you wear the green color shirt, the light contains all different EM waves. Everything will be absorbed by your object. Only the green color frequency spectrum will be reflected. Okay, if you wear the yellow one, only the yellow frequency wave will be reflected. You will see. So that's the way our scanner digitizer to observe the image by scanner. Okay, so they put the light and then on your paper document and then reflect the right color. And we only have these three photo styles. One is the red, the other color is green and blue. And then you respond what kind of color they can respond back from the object. You collect all these three kinds of different major frequency EM wave, and then combine with the color image. So every different color has different wave we just mentioned. For your visible band, very small band, different wavelength, different frequency. We can observe, but in the air, a lot of people like microwave, all the way, radio wave around you, but you cannot see it. Only this kind of wave with a visual band, you can see it. And we have two basic quantity, illuminance, radiance, luminance in the air. Okay, so that's the way our digital camera, our digital scanner can scan the object into the computer. Okay, so you have a photodiode. The photodiode and the energy, reflect energy. You just say there's the light source put on your object, and then it's translate. This is only 1 pixel on your camera, your cell phone. And they test through. There's some filter to filter out what kind of spectrum you like to receive. So I just mentioned, always we have 3 different photodiode for the green color, red color, blue color, RGB. And after that, receive it, and then put its voltage waveform into your device. Okay, every small single cell has given 3 color photodiode to accuracy the signal from the object. The object, you need the radiance illumination, the light source, the way put on the object and reflect. It's I say it is green object, only the spectrum of green will be bright, and your sensor can observe it. Okay, and so maybe sometimes it's a night sensor, sometimes a ray sensor. Like your digital camera, it should be like this one, and this one should be a scanner. You put in the Xerox machine, you scan it. It's a night sensor, goes through like this one. Okay, this is traditional one, slow one. Okay, they have pixel by pixel, go this way, and then 9 by 9 is turning around location to scan your image. Okay, so it's a single sensor element is in the mechanical motion to generate 2D image. Also, you can do 3D image, the same. Okay. If you use some penetration wave, like an X-ray, like gamma ray, so how do they do? They put a different X-ray source and then location, and your object here, 3D object here, and then they penetrate and receive the wave on the other side. So you just return different motion, and then linear move your body inside this one. Then so every segmentation here, okay, every segmentation profile will be obtained, and then once you go through whole body, they will have a 3D image formulated. Similar idea. You need some source first, light source first. Okay. If you give light, you will degrade light. If you give the gamma, like X-ray, the penetrate, and then you have to receive this signal on the other side. Okay, so this is a 3D sensor, and then for 3D actually construct by 2D image, one by one. So they just go there and then rotate 360 degrees, next step 360 degrees, next step 360 degrees, and get every image there, and then concatenate into a 3D image. Okay, so here is the example of digital image acquisition. So we just emphasize again, you need the illumination energy source first, and then put on the scene, the object, and then reflect, and go to your image system here. Image system sensor, and it's an internal image plane, so it's observed like this one. However, every pixel has different intensity level, and how many resolution in spatial image, you have to know your device. Okay, so we have two different resolutions we have to discuss. The first one is your spatial resolution. I just mentioned what's the size. Okay, so you are very lucky because once you touch the digital camera, it's all very high resolution, right? But back to our age, I forgot to tell you the number of the pixel. So in your eye, they have some density number, right? And I remember there should be a 1 millimeter have a 150,000 Hom sector for the density. And on your fovea region, actually they are the size, the square size around 2.25 millimeter square. So actually, when you calculate that one, the Hom number in your main region will be I think around 30 should be 30 something, 31万。I forgot the number. Okay. So the number of the Hom nerve, Hom receptor in your major region is around this number. So that's the reason our traditional frame rate is 640 times 480, right? It's around this number to match with this sector. Anyway, so we say this is resolution, high resolution. So in your megapixels. So different pixels you are going to sample. And yeah, your eyes cannot observe so detail unless you make larger. And every pixel you have different intensity level observed from this image sensor. So this is not an integer itself. It's an analog signal. Okay, it's counting how many electronics are there, and you receive what's the size of it. Actually, it looks like it's like this one. Okay, so if you take a look, the profile from A to B here, A to B here, take a section there, profile, and you will see the intensity level like here. Okay, the whiter is lighter, is intensity level is higher. So definitely for the this background white color, white, so bright, right? Then become dark, then become lighter, become dark, and then be here is white again, right? So for the line sensor observed from your device, signal should be like this. So how you do it? How you do it in your computer to simulate, to do some image process. So first of all, you have to sample it, right? So your image sampling is on different location and depend on the resolution of your spatial resolution. So higher, the width becomes smaller. And once you get it, you are going to read the intensity level for this specific pixels. So it all depends on your intensity resolution. So how many intensity level you are going to quantize or compilation? In Chinese called 量化. So you are going to quantize into different variables. So maybe you are going to have a binary image. If you select binary image, then you will become only two labels, 0 and 1, 0 and 1. So we have to give the spatial holding number there. So what's the spatial holding number? To output to 0, less than the spatial holding parameter, become 0, larger than become 1. So it's a two binary, two different variable binary image. But for this example, there are 6, 7, 8. So 8 different variables. So how you decide it? From here to here, and then separate to 8 different variables. So actually, you only require 3 bits to represent 1 pixel. So we call it an intensity resolution. Intensity resolution. You have to know how many bits you are going to represent every single pixel. If you use 3 bits, every bit is 0, 1, 0, 1. So you have 8 different combinations, 8 different variables to represent each single. So how you transfer this one? So you have to some 7 special holdings. This is called linear compilation. However, you are doing some bootstrap there, non-linear compilation will be better one, right? So your background, white. Do you need a lot to destroy the white? Not necessary. But if you want to do high quality, you are going to not miss any signal layer. You have to think in the other way. For the similar background level, you need more higher resolution to be presented. Because you want to separate every detail. For the edge signal, for the edge component, they already have a large difference. So you don't need a lot of intensity level to separate them because they are already different. So that's another way to call the compression for image compression application. You can have a very good one, but you have very good image for human eyes, but you don't need so many bits to represent it because you can not tell the difference. It depends on your application. So for the linear, much easier. That gives me the equivalent distance between two different variables. And I read the data and I just give some response and then put it into the right corresponding intensity level down. So actually, our image compression in maybe end of the semester, we are doing this one. You are going to say the difference, how to compress it, and then make your visual cannot tell the difference. Instead, the size of the digital image. Yeah, so we have two processes. One is the spatial resolution, spatial sampling, and the other one is the compilation. It's make your intensity level read signal, transfer to some integers. So depending on how many bits you are going to represent one single pixel. Nowadays we use 8-bit. Okay, it's 256 different variable. Yeah, so transfer to that one. You can have like this. Okay, so it's 11 now, so maybe we'll take 10 minutes rest, and later on we are going to define a lot of different terminology to calculate how many objects in that one. So the first homework will calculate what's the connectivity, what's the neighboring, what's the labeling number and the object component. Okay, so take 10 minutes rest.这边暂停。对，对，好，好，谢谢。刚才是哪一个？这个。所以我们结束要把它给关掉。刚才这边为什么杂讯那么多？
是没电。
麦克风哦。
对啊，电池快没电。
谢谢。
老师，那第3章的讲义要
我看一下今天应该是这边太暗了。好。看一下有没有在这里。哦，对，我寄给你了。先看一下，我很多，然后辨析很有趣的，可以帮你改。2个版本，他有帮我改。有头气，没有那么多了，没有改。那个我就。好了，那个我要投可以了，下午或刚有空再。我很好奇，如果先提供这样，对，我真的是要钱。完了啦，反正我也没时间改看，那他还改回来还改的，他改的真的是我，甚至你的写体字没弄。 吧？还有，好，好了，晚上你再提醒我。31、32，哎，没关系，你先扣过来，不然你就可能是，等一下不要关灯好了，我都看不到，这样上应该还好。
那我也把
对啊。我们上次就第一个就是 connect， 以前学过。 过嘛哈，这里嘛哈。
This video may cause temporary hallucinogenic effects.
So now, right? So we have some okay, 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 this round, I look at vision. That tells you not. Yeah. So it's just
But please do not be afraid. These effects usually last a few seconds. Read aloud every letter shown in the screen center. Do not make any mistake.
inside the character.
You can look away now.
No. Third is static image, okay? Right, after illusion. Okay, you can see your eyes, the cone vision, and the broad vision. Try to manipulate the word. Without do anything, just look at this change the background. Okay, so it's optical illusion. So if you see the shape changing, it's fine because you are healthy. Okay, your cone vision and broad vision works. Okay, so now we are going to see some. Sorry, okay, yeah, okay. Is that okay to see the screen? Because I'm going to define some terminology here. So we just mentioned here, we have this digitized sample image here, and we just mentioned we are going to transfer this analog signal into computer. So we need some calculation, and the first one is the intensity. So you see the intensity label changed. So what's the intensity? So we use this function. The intensity we use a function of f. So actually, it's a two-dimensional function, and it's between 0 to infinity. And actually, come from, we just mentioned, is from two resources. One is called illumination layer, I of xy, times reflectance of xy. So we have two functions. One is the illumination. So it's the amount of source illumination incident in the scene object. So we say this is illumination. Okay, so it's from the source, from the amount of source. And then now we have a reflection, R over xy. This is we call it reflectance, the amount of illumination reflected by the object. So reflectance. Sometimes for the X-ray, for the gamma, it's penetration. You have to receive it from the other end. Okay, but for the normal wave, your visual band, they reflect. And we know I of XY is from the light source, so it's come from 0 to infinity. If it's 0, you will see nothing because it's all dark. No source, no light source. But for the reflection function, it's between 1 and 0. So how many percentage, how many amount reflect by your object? Yeah. So for this one, if it's 0, we say it's everything is absorbed. Everything is absorbed by the object, like a white, because the white contains all the spectrum. So the light put on the white, and you receive white, nothing there, nothing object. So absorb, reflect totally. Okay, the white reflect totally, and for the dark, absorb everything, no reflection. So we have two different extreme value. For this one is absorb, and this one is reflect everything, every different EM wave totally. Okay, so it depends on what kind of color on the object. And I just mentioned if it's a green, so it will reflect the EM wave of green color. And if this is a yellow, will reflect the yellow EM wave. So at the end, our value will become luminous from the small one to max one. However, we know it cannot process in your computer. So we are going to have some maxima gradable to define it. So we always use this -1 to do it. So the maxima gradable is digitized to -1. L is the gradable, maybe 256 gradable. So we'll use 8 bit to represent one single pixel. And now it's become maybe this is the popular one, 255, because L equal to 256 EM gradables. Okay, so and we know this is white. Everything reflect. This is black. Okay, so it's gradable intensity contain two components, illumination and reflectance. Okay, so now let's see this one. So we have this quantized value in digital in discrete value quantized, and then we are going to say it is not it's a linear way to do this way. Okay, linear to do this one, but sometimes you can do the linear quantization. Okay, not necessarily equally distance to discretize your grade intensity gradable. Maybe you want to have some more specific detail in a similar background. You can have more different gradable. And for the abrupt change, you only need a small number of the gradable to define it, and the image will be more clear. You can see every detail of it. So it is important to change your quality. Okay. So, but here we are only use a linear gradable quantization. To do it. So this is general way. You can see it's a 2D shape like this one. So here, if we have this image shown as a 2D numerical array here, and you see it's observed change to 0 to 1. Your 255 you can modify, normalize to 1. So it's between 0 and 1, and this is from 0 to 1, and you see the gradable is 0.5, the white color is 1, and the background gray color is 0. So if you use 3D to see the surface, it's just like this one. It's just a standard naming way to see what's the digital image. So every pixel point here, we have different function, f of xy, and here is the center. Maybe you are this is a flow of m divided by 2. This is a m here. Here is a n pixel. Here is n here. So divide by 2 and then take the floor, and you will get the index of the pixel in every location of this image. I think it's quite straightforward. You can skip that one. And yeah, here we just say some image. The label of the gray label of the image sometimes is saturated. What's the saturated? Become highest number of the gray label, so it's a saturation. And for this kind of noise, always in a background, more noise, but you cannot observe, see it. So that's the way. If you use a nonlinear constellation, you can see more detail about the noise. Otherwise, if you use some equivalent, you cannot see a lot of noise there. So I think it's still very straightforward to see. You have different number of the pixel and different gray level of the intensity. So it is the size of the image here. You have different intensity there. So it's 8 bit. Okay, so you have 256, 128 gray level, 7 bit, 64 gray level. So you can see the size is megapixels for you to select it. And this is the N, is the number of your spatial resolution. So you can have different one. It's just say this. You see the size is different to store it. Yeah, it's but nowadays it's no big problem for high resolution. Sometimes you read it, how you read the data. Okay, sometimes 9 by 9, so you have to be careful. Sometimes your software will change it into one dimension, and how you read the data, maybe one column by one column. So it's each column, and then read it from here to here, and then change to here. So you have to make sure you understand how the software reads your image in different direction. Okay, you change the 2 dimension to 1 dimension to calculate 1 dimension vector. So you have to know how they read it. Okay. So let's see this one. This is a different spatial resolution. Now we are going to discuss how about the spatial resolution and the intensity resolution. Are they independent? So what's your expectation? Now we know there are 2 resolutions you have to consider. The first one is the spatial resolution. Spatial resolution is how many sampling points at a specific limit of the range. Okay, maybe high resolution, low resolution to sample. And the other one is how you use how many intensity level to describe your image. Are they independent? So in your image, are they independent? It sounds like strictly independent, right? But actually, if you do some visual test, they are associated. Okay, so here is just an example for you. They are spatial resolution, different spatial resolution. This is 930 dpi. What's the dpi? What's the unit? What's the unit? If you do image processing, you'll see a lot of papers. They just tell you this image is 936. Yeah. The next one, the B image, the right hand side, the upper right, 300 dpi. And for your scanning machine, most of them are 72 dpi. What's the dpi representing? The D is a dot pixel. T is per, dot per inch. Okay, inch is 2.54 centimeter. Okay, so exactly this is the common terminology for the image resolution, spatial resolution, dot per inch. So 930 is in 1 inch, 2.54 centimeter. You have to scan 930 pixels. Okay, in one direction. And for the 1 inch image, the pixel will be 936. 930 times 930 is called 930 dpi. That's for it. Okay. So this is high resolution for 930. This is a very good quality here. This is only 72. So after that, we just enlarge it to the same size and then to compare. So the 672 dpi here, 930 here. Can you see the difference? Can you see the difference? Right? Just look at this number here, 60. Okay, we use the same screen size to watch the different spatial resolution. Definitely, this one is much higher quality than this one. And how you interpret this image 72 dot per inch into this size, the same size of this bigger one, because your 72 dpi should become small one. You just down sampling in the spatial domain. So your image becomes very small, right? From 936 to 72 is only 1/10 of the original one. So it becomes very small size. But now I'm going to enlarge it into the same size of this original one, and then to compare the quality. Definitely, you can see best quality here. How they do this one? We call it interpolation. You already done sampling to a small size, but now you are going to enlarge it to bigger one compared to original size. You have to do interpolation. There are so many different ways to do interpolation. So maybe later on we are going to do bilinear interpolation, the most common one, or cubic bilinear interpolation. And you will see the quality will be much better. But here they use near its neighboring interpolation, the easier way to emphasize the difference. Okay, the very lazy way to enlarge the size to the same comparable image size. So this is the spatial resolution. I just want to emphasize this one. So the spatial resolution will change the quality. So you downsampling your spatial image into a low resolution, the quality becomes bad, right? So that's our intuitive imagination, our intuitive knowledge. You have a higher resolution. Your image quality is better, right? Suppose, okay. Now we are going to change the intensity level resolution. What's the intensity level resolution? The left-hand side is the original one. This is a 256 level image. 256, which means how many bits for one single pixel? How many bits? 8 bits, right? 256 gray level, different gray level. So 1 bit, you can present 256. 2 to 8, right? 2 to 8. To be very straightforward, you have 8 bits. Every bit has 2 different binaries. So total different combination is 2 to 8 power, 2 to 8, and 256 different level here. So it's a very high quality image in your, it's the same size, 2022 times 80, the size here. With this gray level, 256 for each pixel. 1 8 bit to represent one single pixel. So different for here. Now we are going to downsize. This is only use 7 bits. So this image only have a 7 bit different intensity level. So how many gray level? 7 bits is 1 to 128 gray level. So let me enlarge this too. Please tell me, can you see the difference? Impossible. You are not Superman. You cannot see any difference between these two images. Actually, our eyes cannot. That's why our eyes only can recognize maybe 20, 30, some different levels at a time. Okay, roughly. But here, sorry, it's not that easy to make a difference. And now, this is 6 bit, so 64 gray level. Can you see the difference? Still, it's hard to see. Okay, 64 different gray level. Through your eyes, compared to this one, okay, still good quality for you. This is 5 bit, 32 gray level. Maybe some blur you can see, some blur. But compare these two, still good, right? Still good, right? 32 gray level, Okay? So good. That's what I told you. Your image, your vision, not tell too much difference. When you download, separate your intensity level. Okay? The same resolution, spatial resolution, but different intensity level. But if I change to 4-bit, this one, something occurred. How's that? See that one? Some force control appear. Okay, so if you look at the textbook, very clear. How about this one? Even clear, right? Because force control. How many bits? No, 3 bits. So when you come to 4 bits, 3 bits, some force control getting clear. You see something different. Okay, this is a 2-bit 4-grade level. Okay, very clear. Some force control there. Okay, and for the binary, 1, 0, 1, 8, only 2 different. But they use grade to represent. Okay, then now which color you select. So only 2 grade level here. So what do you see? What's the quality of the image? So they try to evaluate, is there any association between the spatial resolution, the size of the image, and the intensity resolution of the image. So they do some experiment. This is the very famous one. Okay, so there are 3 images. The left one, very famous one. The Lena, she's still alive, very healthy. And she is the woman who contributed a lot for the image compression. So she is the cover page girl of the Playboy. In the HP, a lot of engineering, actually one is exciting and very some good compression techniques. So it's always our model. Okay, we do this yeah, even the textbook use this one. And we are going to put 3 images here. So what's the difference between these 3 images? Anybody can observe. What's the differences among these 3 images? So you can tell me a girl, a gentleman, and gentleman and girls, boys. No, that's not what I'm going to say. It's a parallel image. It's a cameraman. It's a Lena. Okay, so they all very famous image for image processing. The left one is very simple content. The middle one is the middle compressive content. The right one, is complex. It's a lot of complex detail. Medium label, simplified label. So just tell you 3 different labels of the content of the image. And you are going to do some resolution experiment. So we are going to change the different N and different L for these 3 images and evaluate their quality of the image. So how do you evaluate quality of the image? I will just learn some experiment in previous image. I keep asking you, are they the same? Are they the same, right? And I do some modification regarding the intensity level, and then do some modification of the resolution, and then ask you to compare. Are they different? Are they similar? Are they equal? Right? So the same. They do on these 3 images separately, and ask the viewer, ask people to see, are they same quality now, or are they getting worse or getting greater? So after this experiment, they observe this result. We call it representative isopreference curve for the 3 types of image. Okay, so we have the face, the lady, camera, the car. And every solid line represents the ISO preference curve. What's the ISO preference? ISO is the equal, right? Preference is you like favorite. ISO preference, which means equally good quality for your region. Okay, so the vertical is the spatial resolution. 32, 64. Oh, sorry, this is the spatial resolution. The K is the bit, different bit. Then try to show this ISO preference of each image, and the result come up like this. So you can see when your image become more simplified, select this curve. When your image, okay, select this curve. When your image is very complex in detail, select this. Their ISO preference will observe like this one. So what's the result to explain this kind of experiment? To me, just when your content of the image is very complex, okay, it doesn't matter when you change the gray level resolution. You cannot see the difference. It's very complex detail, complex image inside. Doesn't matter. But if you have a straight line here, okay, when you have the same spatial resolution, but sometimes lower intensity level get better for your eyes. Why? So they have to do some this kind of psychological experiment. The reason you try to explain is if your image content is quite simple and you use less gray level to represent it, you will enhance the contrast. That's the reason. When the content of the image is simple, not so complicated. Sometimes you reduce the gray level. You draw down the K, the bit level. The quality will be better because enhance the content. Region like it. Okay. So when it's a complex, complicated, the matter, dependent. So that's what it is very try to explain. The resolution between spatial and intensity level still matters, not independent itself. Okay, so the ISO preference line can tell you the result. Okay, so it's a way. When you reduce it, you are going to do what? You are going to recover it, right? Sometimes you only got the lower intensity level of the image, but you want to enlarge in this big screen. I'm going to interpret the data inside the image becoming larger. Otherwise, just like our previous one, say this is 72 dpi. Okay, per inch, and then when you magnify, enlarge it in the big screen, just like this very bad quality. So how you do it? How you do it? So traditional way, when you have a low quality, you are going to do some interpolation. So this is after different interpolation from the 72 dpi. Put it into a large screen and see exactly the same bad quality small image. We enlarge it and put it on a big screen, but this quality much better than the previous one, right? How do we do that? Very easy. Just do some linear interpolation. So actually, we have this is the lazy one. This is the lazy one. How you do it? Nearest neighboring interpolation. Nearest neighboring. So, for example, How you do it? You just, is that easy? Very easy. Nearest neighbor. I just find out the nearest neighbor and then put the data inside. The 2 by 2 will become 4 by 4 immediately, right? So nearest neighbor, easy one, but it's not good. It's not good. So how can we do this one? Let me add one more. Okay. So you can do some interpolation. Depend on your neighbor pixel value, and then not exactly just put on the constant to your neighboring one. So the previous one we call it a nearest interpolation. Oh, it's bad. Okay, so we can do some bilinear interpolation. How you do that one? Okay, so suppose we have a signal, one-dimensional, not two-dimensional. Okay, one-dimensional. I have a signal like this one, and I have the first data here, the second data here, the other one, and this is we call x1, x2, and now we try to find out this one in the between, maybe call x. So what's the value here? So it depends on the distance, your different weighting. So you are going to interpret one single pixel value here. This is the value, function value. So can you tell me what's the value for the x? How you do that one? So we know, if we know, it's our function y here. Oh, it's a y here. It's x here. Okay. So we try to find out this value for the x location. So we use from 1D to 2D. Okay, 1D first. Later on we have a 2D. For this one, this function, you are going to interpret this data inside there. So how you do that one? So we know y equal to f of x, right? The function of the x is what's the x, and you give the y value, the function value of it. So we are going to write down this one. If y minus, this is y1, this is y2 for this point, x2, y2, x1, y1, f1, f2. Try to find the f of x for the y. So we have y minus y1, y minus y1 here, compared to x minus x1, compared to x minus x1. So this one compared to this one, actually it's equal to what? y2 minus y divided by x2 minus x. Is that okay? So it's like this one, because linear, we say the linear interpolation. So this one compared to this one equal to this one compared to this one. Can you agree? It's a linear, right? So this portion, y minus y1, divided by x minus x1, equal to this one, y2 minus y, divided by x2 minus x. So easy, linear, because I'm linear. Even I know the original function, the blue line is nonlinear, but now you are going to interpret the data between x1, x2, y1, y2. So you must think about the easy way. So we use a linear interpolation. So from here, you know, we can get this result. From this equation, easily you can get y equal to what? Could you please help me to write down y equal to some y0 plus something times y1 times y2. So you just manipulate this function, cross production, and then summarize together. Actually, the answer will be y equal to x2 minus x divided by x2 minus x1 y0 plus x minus x1 x2 minus x1 y1. Okay, from here you can derive here easily. So it's a bilinear interpolation in one dimension. Okay, so this is in x direction. I'm going to do this one bilinear interpolation in x direction. So if I give you the new data of this one, we say this is x direction. So we can write easily in x direction. The linear operation become f of r1 equal to x2 minus x, x2 minus x1, f of q11. If I define now two dimension, okay, let me define two dimension. So we have a 4 point to find out this new pixel here. So we have a 4 point here. It's a q12, q22, q11, q21. So try to find out the p, the linear interpolation for the p pixel here. So for the one dimension, it's easy because you have this one, right? P in x direction here. Again, for the y direction, it's just like between this one, and the y direction. So we just do it twice. Seriously. Okay. Do twice. So bilinear interpolation for two-dimensional. The same, exactly the same as one dimension. Okay. So in this way, so we say this is R1. So if you project this one here to x direction, we say this is R1 here. And if this is to here, is R2 here. So we have this one. If you look at this one, R represented by these 2 points. So, and the rate from this equation exactly the same. X minus x1, x2 minus x1, and this is f of y1 is q21. I hope you can follow this one. I just consider these two in one dimension, and then linear operation, interpolation for this point. They use this equation correctly. Here, y0 becomes here, y1 becomes here. So y0, y1 here, right? You take the same previous one. And then you look at the vertical line. So vertical line again. So FR2. This is FR2 here. So again, exactly the same. Not vertical, horizontal line. Okay, this is horizontal line. So calculate, copy this one again. And this become Q12 plus. This is the same parameter 1, x2 minus x1. This is the f of q22. Okay, so see, I have this R2 and R1. Use one dimension in x direction, right? Twice, exactly. This for R2. This for R1. This for R2. Okay, if you give me 2 points in the neighbor in x direction, for example direction, I can calculate how you represent by interpolate by these 2 points. This one interpolate by these 2 points. Immediately, right? Now we are going to do what? P, and P is equal what? R1, R2 to present it. By linear, it's interpolate in y direction, vertical direction. So just do the twice, and you will get how to represent the P by these 4 pixels. Okay, so the result will become like this one. So f of P equal to y2 rotate. Okay, y2 minus y. So quickly, y2 minus y, y2 minus y1, fr1 plus y minus y1, y2 minus y1, fr2. So please look at in this direction. This direction. And the R2, R1 is in the y direction. So see, previous you got this one, and finally you can get f of xy blah, blah, equal for easy to get this representation from the four neighboring points. We call it bilinear operation. But you can use some easier way to do this one. It's just a process. Make you understand how you do it. But you can use even easier way. How to define the bilinear operation here. Actually, this point is represented by 4 points of your neighbor. So you can just write the final solution of this one. Actually, you derive it. It will become like this. A new xy will become bilinear operation is this result. Ax plus by plus cxy bilinear. There are 2, 3, 4 coefficients to calculate. Every single point located in four points of the data, and you want to try to use bilinear operation to represent it, you can write down this equation immediately. And the only thing you have to calculate is the equation of this relationship. So let's use one example. Okay, how you do this one? Okay, for example, let's see, easy example here. We have a 4 point here, and this is the first point neighboring, second neighboring, third neighboring, fourth neighboring, and we have a value of this one is 10. Grade level is 10, and the first pixel is located 1, 2 coordinate, and this one is a 2, 2 coordinate. Okay, just example. Okay, 15. Oh, sorry, 15, and this location is 2, 2, and this is the number is 4. Grade level is 4, located at 2, 3, and this second neighboring is the label is 20, located at 1, 3. Okay, so we have a 4 point. Now we are going to calculate this one. Vxy. What's the label for this one? I can give any location within this 4 point neighboring point. Please tell me what's the linear interpolation by linear interpolation for the value of xy here. So I just tell you, we have this after you calculate, you have this format, and we need to calculate A, B, C, D for the data. So how you do this one? So you just put into the 4 point into this equation, and then try to formulate 4 different equations. So we will do that one. The 10 point is evaluate 10, and what's the relationship between this one? So their data will be A plus xy is location of this coordinate. So A times 1 plus for the 4.1. So you have to put all the xy coordinate into that one, and B is 2, so it's B times 2, plus C times xy is 1 times 2, plus D. And for the second point here, their relationship will formula like this one, and it's become 20. A times 1 times plus B times 3 plus C times xy, E1 times 3 plus D. And for the third one equation, third point, and it is 15 equal to A times 2 plus B times 2 plus C times 2 times 2 plus D for the fourth point here. So the value here, so they can have this 4 equal to A times X is 2 plus B times Y is 3 plus C times 2 times 3 plus D. So see, I have 4 different coefficients and 4 equations. You can solve this union function, and then finally you find out the ABCD will be. I don't have the answer yet. Okay, so you can find out ABCD here. So put there, and every location is this one. You can just calculate by the xy here, and then A you know, C you know, what's the value for this interpolation for this. This is the other way to see bilinear interpolation. Okay, and also you can have a cubic bilinear interpolation. You can use 16 neighboring points, even higher, even more neighboring pixel to calculate. So we call it cubic is bicubic. We are not going to do this one. A lot of tools. You just select. But you just know what's going on there. If you want good visual quality, from small size of the resolution into a better one, and you can apply different interpolation technique. The nearest neighboring is the worst one. Okay, so see, you have a 16 parameter you have to solve, and it's like this one. It's become more complicated because your neighboring will have a 16, 0 to 3. So you use all the 16 neighborhood pixel to decide what's the value you should put a new interpreted data. Okay, so it's just let you know you have some sampling process, some sampling. Sometimes you are going to back up sampling, so you have to recover the image into a certain size. How you make the image better? Okay, so from here to here. This is the bilinear. This is a cubic bilinear interpolation. So the quality better than this one better than the nearest neighbor. Okay. This is not our homework, no worry. Too much mathematics. I'm sorry, I don't get delayed because today I want to introduce connect component. It should be easier. Okay, so next we'll do it Wednesday. So you will learn what's the neighboring pixel. So it's just the image resolution, spatial resolution, intensity resolution, and you also evaluate your eyes today, right? So the time is up. So we will do it on Wednesday. We'll teach you how to use different distance definition. We have a lot of different distance. Okay, if you are going to talk about what's the Manhattan distance, what's the chessboard distance, what's the Euclidean distance, all different results. So the first homework will teach you how to define the distance and how to get the connect component from the image, from binary image. Okay, easy one. For example, you are going to do some object vector definition, and you have to find out the object first. So object, which one is connected to the other one, and which stroke should be connected together. You have to find out the component first. Okay, and after different definition, there will be different answers. Okay, so we are going to learn chessboard distance, Manhattan distance, Euclidean distance. Okay, so let's find the next test. Okay, if you have questions, please stay. Otherwise, our class will stop here.这我的动作。这是用什么录？
Teams。